Morning. Hope you all are doing all right today. All right, did you have any questions over section 6.4? Okay. Well, for the graph problems, let's see, 73, this is page 462. We have f of x is natural log of x plus 4. Our goal is to sketch the graph. Now, natural log, log base 2, log base 3, they're all kind of similar in shape, because this is log base e, and e is a number that's between 2 and 3. And we look at this in terms of the transformation. So here's our basic graph right here. We know our anchor point is 1, 0. On the left, as it continues left, we have an asymptote, and it goes up and over to the right. So we can graph this one using the transformation. Now x plus 4, that moves everything to the left 4 units. Remember, it's always opposite inside. So f of x now, the function we're trying to graph, now our anchor point starts here at 1, 0. We go left 4 with that. 1, 2, 3, 4. Our vertical asymptote moves left 4 also. 1, 2, 3, 4. And so as it continues down to the left, and then up and over to the right. So the same shape, we haven't changed the shape at all, but we've taken everything and moved it left 4 units. And so our domain is from -4 to infinity, and the range is all real numbers, which for a logarithm the range will always be all real numbers. Oh, I'm sorry, I didn't want you to worry about the inverse. Yeah, it's really A, B, and C that we need to do there. I didn't notice we had those other parts there. But yeah, don't worry about the inverse. Okay. So on 75 and 79, it is really the same thing as we're doing here. It's just the vertical and or horizontal shifts being applied, and then just move everything accordingly, including the asymptote. But otherwise, that's all there is to it. Yeah. Okay. So we had 91, 95, and 97. Let's see, 90. Now, each of these, the way that we solve, 91, 95, 97, is they're currently in logarithm form, but we solve them by converting it to exponential form. We're going to look at a different approach in today's class, which may be used for some of these, but not all of these. But anyway, on 91, we have log base 2 of 3x plus 4 is equal to 5. Now we convert this to exponential form. I can go ahead and do 79, yeah. Now, when we convert this, again, we take our base 2, this is the base of our exponent now, and then raise it to the 5th power, and then equal to 3x plus 4. Okay. A lot of it's just recognizing that pattern. Base raised to the opposite side equal to the argument of the logarithm. Now, 2 to the 5th power is 32. And so from here, our goal is to solve for x. So we can subtract our 4 over. 28 is equal to 3x. And just divide by 3, so 28 over 3 is equal to x. Main issue here is in the conversion from logarithm to exponent, and that's the conversion formula we looked at last time. It's really just a rearranging of the terms in a specific way. So until you get comfortable with the pattern, then it might be easier to go through and look at this and say, okay, log base b of x, is equal to y, and that converts to b to the y equals x. So we take our base b, 2, raise it to the y, 5, and set it equal to x, or 3x plus 4. And that's how we're converting that. It's according to that formula. If you practice it enough, you start to get a feel for it, like as far as the pattern that's happening, and you can just rearrange it yourself and not worry about it. But until then, I do recommend, like what we're talking about here, just kind of lining up the values, like, okay, here's b, here's y, and this is quote-unquote x. It's actually 3x plus 4. But then we change it accordingly from there. But the big thing is here, once we get to this form, now we can actually solve for x, where we couldn't solve for x up here. And that's why we converted in the first place. Is if we can't solve for x, or whatever unknown we have in the logarithm, then we try converting it to an exponential. 75. 79, sorry. I already forgot which one you asked for again. F of x is log of x minus 4 plus 2. What base is this logarithm? Since it's not related. Yes, this is base 10. Alright, I was just throwing that out there. So we look at this logarithm and we have two shifts that have taken place. This is a shift right of 4 units and a shift up of 2 units from its original location. Now we know our graph starts off, our anchor point, 1, 0. So we take that point and go right 4. A lot of control of my axis there. And then up 2, so 1, 2, 3, 4 right and up 2. And the vertical asymptote, which is starting off on the y-axis, that moves to the right 4 also. 1, 2, 3, 4. And so we draw our vertical asymptote. Mainly the bottom half is what we need there. And then we draw in our basic logarithmic curve. Okay. So we're just shifting everything left, right, up, and down as we need to, and that includes the asymptote. So our domain is from wherever the asymptote is to infinity, so 4 to infinity. We never actually technically get to 4, so we put a parenthesis there instead of a bracket. And then a range, as always, is all real numbers. Okay. Good, good. Let's see, 95 was the next one. Natural log of e, I believe that's an x. Yeah, natural log of e to the x equals 5. Like that. There we go. What is the base of the natural log, ln? We know the base of log, with, if there's no base written, this is implied to be 10. But we have a similar situation with natural log. E, yes. This is log base e. Okay. So log with no base is 10. Ln with no base is e. It's important we remember the difference there. Now, we can do a conversion here, but we actually have I'll show you a formula that we have regarding this in a moment. But if we do our conversion, or convert, sorry, we take our base, raised to the opposite side, equal to the argument. So we get e to the 5th equals e to the x. Now, this particular equation, we're solving two exponents equal to each other, exponential terms equal to each other. Goes back to what we did in the previous section, which says if we have the same base on both sides, then the exponents must be equal to each other. Now, technically we don't cancel out the base, but basically we cancel out the base. So we end up with x equals 5, and that's our solution right there. Okay. We actually have a property that says log base b of b to the x is equal to x. And b raised to the b to the x, or log base b of x, my bad, is equal to x. Now, it turns out that logs and exponents are exponentials. These are inverses of each other. Now, what an inverse does is that they cancel each other out. So, for instance, if we multiplied something by 2, then the inverse would be to divide the result by 2. It gets us back to our original value. Okay. Same thing here. If we raise something to a power, the inverse is to take log of that base, of that log with the same base as the base of that term we raised to a power. Log and that exponential cancel each other out, so it's just x equals 5. Okay. And even if the order is reversed, that the x, base b is raised to this log of base b, those still cancel each other out. It's just x equals x. We don't have to use those properties, but if we can remember them, it does make a few things a little bit easier. A little bit of a shortcut in a few cases, but even if we don't know those properties, we can work around it and come up with the same answer like we did here. Okay. The other problem was 97. Log base 4 of 64 is equal to x. Now, there's actually a couple of different ways that we could work this. One way would be to convert. So we get 4 to the x equals 64. And this also becomes a question like in section 6.3, our first section we did in this section, or chapter. 64, can we write it as base 4? So if we can get base 4 on both sides, we can simplify this, or solve for x. 64 turns out is 4 to the third power. Cancel out the common bases, and so we get x is equal to 3. Now the other way that we can go here is we can use the change of base formula. It says that log base 4 of 64 is equal to log of 64 over log of 4. Now we can just put that into our calculator and show that we get a result of 3. Okay. So whichever way we do it, we still get the same answer, 3. Technically, change the base formula is actually in section 5. I like to go ahead and introduce it here because I think it fits better. with this material than with the other material. Anyway. Other questions? Let's see what I missed. 17. Amanda, you asked for that one. Oh. 17, we have e to the x equals 8. Now, let's see. The instructions here, they want us to rewrite this as a logarithmic expression. So we want to take an exponential and convert it into a logarithm, which is this approach: b to the y equals x converts into y equals log base b of x. So here's b, here's y, here's x. Doesn't make a whole lot of sense that we have two different x's, but remember which one we're replacing where. So when we convert that, we take our y, which is x. We have log of base b, which is e in this case. And then x goes inside the logarithm, that is 8. No, it does not, that's really just for trigonometry that's an issue. Sines, cosines, tangents, and the like. At this stage, we're not going to worry about it. Alright, now the only other thing we need to do here in problem 17, we converted it successfully, but log base e, there's an easier way of writing that. Do you remember what that is? Log base e is a specific logarithm. Natural log, yes. So we can rewrite this as natural log 8. Is that what it says in your calculator? August? Usually, if you see log e, that'll be the same thing as natural log. There's nothing else it could be. Yeah, sometimes you see regular logarithm are written as log 10. Yes, that's correct. It doesn't have both, does it? We have two different, you have log e and you have ln as two different buttons. That's kind of strange. You could try it out and see if natural log of 8 is the same. Okay, I got you. Okay, that's right. That's what we normally have. Sometimes you will see log e instead of ln, but more often you'll see log 10 instead of just log. This natural log is very specific, but log by itself is not quite as specific because the base there we know is implied to be 10, but it's nicer when it says it outright. Now, Brock, I think that might be for that's for you to use another base besides 10 or e. Like I have a similar function on this calculator. Oops, let me clear out of that first. This is log base, and not quite sure how to use that. I guess I could test it out. Might be a comma I have to do. Or parentheses. I'm not quite sure of the format. Yeah. Anyway, I might have to do like 2. Oops, that's not how it is. Yeah, I don't know. That's the kind of thing you want to read the manual for and sort out. But that's probably what it's for, is to be able to find log of different bases. So you don't even have to use change of base formula. You can just find it directly in the calculator. If you can figure out how to use it. I don't know how to use mine. Alright. The last one was 39. We have f of x equals natural log of x minus 3. And we want to find the domain. Now, finding the domain of a logarithm just from the function itself, again, the key element here is whatever is inside the logarithm function, specifically the argument here, that must be greater than 0. So whatever is here, just set greater than 0, and we can solve for x. And that's our domain right there. So x has to be greater than 3. This is just one section, August. It's not time to panic now. When you think of it as a chapter, it's a little bit more imposing. But, you know, you just gotta keep practicing it and keep an open mind as far as you know, not go into it with the attitude of I don't like this, I don't understand it, I'm not going to enjoy it, or whatever. The main thing is to, you know, not fall into that mode of thinking where it's just not something you can understand, but give it a chance and see if you can work some problems and figure it out. Mm-hmm. Or ask me for help, absolutely. Yeah. That is in fact what you all are paying me for. All right. Excuse me. Okay. So in section 6.5, we're talking about the properties of logarithms. Wow, that's counterintuitive, but if that's how it works, man, that's good. Okay. There's really four different formulas or properties I like to talk about in this section. One of them we've already covered, which is the change of base formula. But now we have what's called the manipulation properties. And we call them the manipulation properties because it allows us to take logarithms and move things around, combine them, split them up, and just do different things that allow us to better be able to solve equations and similar. First of all, we have our addition rule that says that log base b of x plus log base b of y is equal to log base b of x times y. Now our second property is actually very similar to that one. It's just subtracted instead of added. And if adding two logarithms led to log of a product, what do you think subtracting two logarithms will lead to? Divide. Yeah. So log base p of x minus log base p of y, we can combine them into a single logarithm of base b, and it's just x divided by y inside. This actually gives us a significant advantage of working with logarithms, and really expands the situations where we can apply them and successfully solve equations. Now there are times that we want to take logs in this form and split them up. Most of the time, though, we do want to be going in this left to right direction, where we're actually combining the logarithms together. Now this third property, depending on the scenario, we do tend to use it more in both directions. And this says that n times log base b of x is equal to log base b of x to the nth power. Now this says that if we have a number multiplying our logarithm, we can bring it inside as an exponent on that term. Or if we have an term raised to a value, we can take that exponent and factor it out as a coefficient. This one, unlike the others, we tend to use both directions depending on what we're trying to do. But those are our three manipulation properties. And so we'll look at a couple of problems in this section where we want to take these multiple logarithm terms and combine them together into a single term. And then we'll look at, we'll move on to section 6 where we actually solve more equations utilizing that approach. So let's look at this is 58 on page 472. So the problem is we have 2 log base 3 of u minus log base 3 of v. Okay, now ultimately our goal is to express this as a single logarithm. Now, to combine these into a single logarithm, we know we have the subtraction here, so we can use our second property, second manipulation property. However, there is something else that has to happen first. Notice that when we stated these properties, there were no numbers in front of the logarithms. If there is a number in front of the logarithm, we have to move it up inside. Okay? That's always our first step. Before we can combine logarithms together, whether they're added or subtracted, any coefficients have to be changed to terms inside the logarithm. So this 2, we can start off bringing it up inside. So we have log base 3 of u squared minus log base 3 v. Now that we got rid of the coefficient, we can combine them together and divide the two terms, u squared over v. Notice that we have just a single logarithm now, but now a quotient inside. Whenever we combine two logarithms, we just have one logarithm, but we now have multiple terms inside that logarithm. And that's how the change is made. It actually allows us to do some useful stuff further down the line. Not necessarily in this class. This class we're just getting the hang of learning the properties and solving a few equations with them. But yeah, we'll get to do some different things with this in calculus and other classes, which doesn't. I mean, it's not a major thing, but again, it really expands the different types of equations that we can work with and solve, which is nice. Okay. So let's also look at 62. Here we have log of x squared plus 3x plus 2 minus 2 times log of x plus 1 Now, same situation. We want to be able to combine these two logarithms. Currently they're subtracted, so we know we'll be able to combine them by dividing the arguments. However, first thing here, we have this 2. So we're going to take this 2, move it up inside. Okay. This 2 gets shifted over here. Now that we've gotten rid of the coefficient, we can combine them together. And so this will be log of x squared plus 3x plus 2 over x plus 1 squared. With logarithms, I'm not entirely sure. Logarithms are an entirely different beast. A lot of the things that were discovered mathematically were really found because the science of that day needed an easier way of calculating certain things. So in ancient Greece we have geometry, which there are some relations with that with algebra, but not exactly, but it did lead to some algebraic results. In ancient Greece, I think that's when they discovered the concept of irrational numbers, which is directly connected to working with the Pythagorean theorem, I believe, is where that came from. Anyway, the Pythagorean society, the followers of Pythagoras, this is blasphemy to them to suggest that a square root of 2 is an irrational number, that it even existed. Okay, which kind of tells you the level of math we were at back then. But this is like 400 BC, 350 BC, that era. So, golden age of Greece, but you still have naysayers. But it wasn't exactly the Enlightenment yet. So, educational institutions in ancient Greece were basically rich kids going to listen to philosophers talk all day, at least part of the day. Because these were the kids that didn't work in the fields and work in food production or labor or things like that. These are the people from rich families. So they get to hang around and listen to these guys, and they each of these philosophers or mathematicians developed a following of sorts. So Plato, all those guys. But then we also have Pythagoras. You had the Pythagorean Society, or whatever you want to call it. But these are just the students mainly. They become a little bit insular, as happens with people involved. And so, things back there were crazy things back then. Then you flash forward to the Renaissance era, and we have so much more math happening then. A lot more algebra, a lot more calculus, and a lot more applications of science. A lot of the science in the Renaissance was made to aid the scientists of the day, astronomers like Copernicus, Galileo. Although Galileo is not quite in the same era, I think, as some of the others. Maybe off by 50 years or so. But anyway, so algebra has a long history of development and refinement and things. Napier, who created logarithms, I think came a little bit later than most of the others. Is probably in our book as a kind of side note here. See if I can find it. Okay, apparently our book doesn't have a lot of history notes. My calculus book does, but not our algebra book. Anyway, I think he came a little bit later, like maybe even as late as the 1700s, which was much later than the Renaissance. Anyway. But yeah, the driving force behind a lot of things is science and what the scientists needed to do to complete their work. And that's where the mathematicians came in. Nowadays, it's still the same to a certain degree, but a lot of the research in mathematics is also on the theoretical side, which may not ever be used for anything, but a lot of it is used to demonstrate why we can do certain things. Alright. We're not quite done with 62 here. I kind of went off on a history tangent, but that's okay. By the way, Pythagoras probably didn't discover the Pythagorean theorem, but it was one of his students that did. But because they're his students, he gets to take credit for it. That's actually when you look at the graduate university system, and actually some of it's the same. Like if a graduate student's working under a professor, sometimes the professor does get credit for that discovery, depending on their involvement. So that's still not that unusual, but to give sole credit to Pythagoras, that was pretty unusual back then. So it's like even when I wrote my master's thesis, I still had my two supervising professors' names attached to it. So. All right. Now the reason we're not quite done here is we've combined it together as instructed. This can actually be reduced. Not always, but we always want to check if this is possible to reduce. So x squared plus 3x plus 2 can be factored, and one of those factors happens to be x plus 1. So this is x plus 2 times x plus 1 on top. And this is x plus 1 squared on bottom. So what we can do is we can take this x plus 1 on top and cancel one of our x plus 1's on bottom, so that we end up with log of x plus 2 over x plus 1. And that would be our answer. So whether they're added or subtracted, we are able to combine them together. We just have to make sure if there are a coefficient, or is a coefficient, then we have to move it to the exponent inside before we combine any logarithms. Alright, let's move forward to, and that's really all I need to cover in section 5, is just kind of the basic properties here, and these two work basically the same, so I didn't necessarily need to work both of them, I felt, but I wanted to make sure I demonstrated this one. Anyway, so we move forward to section 6.6. This is on logarithmic and exponential equations. And here we learn how to solve other equations using exponents and logs. Now, let's see. Let's look at logarithmic equations first, and there's a few others that we can work now that we've looked at section 6.5. There's really two situations we have to look at, but step one is if we have multiple logarithms on one side of the equation, we can combine those together just using our properties from 6.5. That's our first step, is to combine them. Second, if log base b of x equals log base b of y, that implies that b is equal, or sorry, x is equal to y, not b. And this is actually very similar to an exponential property that we used. Basically saying if we have the same logarithm on both sides, then their arguments inside must be equal to each other. X equal y. And the third rule says if log base b of x is equal just to some number, then we convert and solve. So that's the general process that we use to solve these logarithmic equations. If we have multiple logs on one side of the equation, we combine them. If we then just have log equals log, then we solve what's inside them to each other. And if log equals a constant, then we convert and solve. Okay. Now, one thing I want to add is if we apply this first rule, we always check answers for validity. Okay? Because one thing that happens when we combine these terms is that sometimes we create additional solutions, much like when we square both sides of an equation that has square roots in it to begin with. So we had to check them then, and we have to check them here. So there will be problems where we get two solutions, but only one of them is actually valid. And the reason a solution might be invalid is that if it's like log of a negative number, because we know the domain of log functions is positive values. We can only evaluate logarithms for positive values. So if we plug an answer back in and end up having to take a log of a 0 or log of a negative, that means it's invalid, and we can cross that one off. And there are even certain equations where there is no solution, where we might even have two solutions that we find, but it's possible both of them are invalid, so we have to make sure we check everything. Now, the only time we really have to worry about that is if we're combining terms, but it might be good in general just to always check for validity, just for our own sanity's sake. Making sure everything's working. Alright, this is page 478. Number 6, we have log of x plus 6 equals 1. What is our base here? $10, good. Now, if we have logarithm equal to a number, we convert and solve. So log equals a number, we convert and solve. So converting this logarithm to an exponential form, take our base, 10, raised to the opposite side, 1, equal to the argument inside, x plus 6. So 10 to the first power equals x plus 6. And now we can just solve this for x. 10 to the first power is just 10. And then to solve for x, we just need to subtract the 6 over. And so 4 is equal to x. And if we plug in 4 plus 6 is 10. 10 is positive, so that checks. That's what we're looking for when we check our answers, is that we have log of a positive number. Because that's entirely where the domain changes. If we don't have a positive number, then the log of that value does not exist. Okay. Looking at number 10. Log base 5 of 2x plus 3 equals log base 5 of 3. Now this time we have the other scenario where we have log equals log. That's option, or that's our second step or option here. And so if we have log of the same base on both sides, then essentially we can cancel out that logarithm and just say whatever's inside has to be equal. So we can get rid of log 5 and say 2x plus 3 equals 3. Good. Now, it's important that we don't get carried away with this idea of being able to cancel out a logarithm. And we're not technically canceling out, but effectively we're getting rid of those logarithms, which really, no matter what you say, it amounts to the same thing. But it's only under very specific circumstance that we can do this, which is this specific circumstance here. Logarithm of one thing equals logarithm of another thing. Those are identical logarithms. We can get rid of them. Right, we subtract the 3 and then divide by 2, we get x equals 0. So the question is x equals 0 valid? Well, if we plug in x equals 0, we get 2 times 0, 0, plus 3 is 3, and 3 is positive, so we're good. So notice it's not x itself that has to be positive. This expression has to be positive after we plug x back in. And that's an important distinction there. There's no x over here, so we're okay with that one. Any questions on these two? And really, this illustrates the two different types of equations we can end up with. Log either equal to a constant or log equals log. Now, we're not going to try to confuse you and put log of two different bases here, so don't worry about that. If we did, we wouldn't be, well, we would be able to solve it, but it'd be much more difficult. And we don't want to worry about that right now. I don't want to worry about that right now. It does involve the change of base formula. Alright, so there are a couple of other scenarios I would like for us to look at, though, with these logarithms. And that's specifically incorporating this first rule, where we may have some answers that are invalid. I want us to make sure to go over a couple of those. We'll look at 20. Two times log base 3 of x plus 4 minus log base 3 of 9 is equal to 2. So this is really our third scenario where we have multiple logarithms on the left-hand side equal to a constant on the right. So we can combine the two logarithms on the left, but before we can combine them into a single logarithm, what else do we need to do first? Make the 2 here an exponent, yes. So this 2 can move up inside. So log base 3 of x plus 4 squared minus log base 3 of 9 is equal to 2. Now after this, we can combine our logarithms. If they're subtracted, how do we combine the terms inside? Divide, good. For 9 is 2. Now we have log of one expression equal to a constant. And so this is where we come back to these two rules, 2 and 3. Since we have log equal to a constant, we still have to convert and solve. Convert. What I think I'll do is I'll move that over here just to conserve vertical space. Our conversion, again, we take our base, 3, raise it to the opposite side, 2, equals x plus 4 squared divided by 9. So base raised to opposite side equals argument. If we do enough of this, we might get a good hang of it. Now 3 squared, it's just 9. What can we do next to help us solve this? Yeah, well, we can't really... Yeah, we can't exactly cancel the 9. We want to cancel this 9, though, for sure. And we can do that by multiplying by 9, exactly. So the multiplying by 9 cancels this one, and then multiplies this one by 9, which makes it 81. How do we solve this from here? This goes back to all the way to chapter 1, or 2. First set of material. Chapter 1. Oh, we still have to solve for x. Take the square root of both sides, exactly. So we can take plus or minus the square root of 81 equals x plus 4. So plus or minus 9 equals x plus 4. This is where we branch it off into two equations, because we have positive 9 and negative 9, which will give us two different answers here. Guess I need the whole page after all. This is kind of a big problem. So we get x plus 4 equals 9, and x plus 4 equals negative 9. And we just solve these by subtracting 4s in each side. So x equals 5 and x equals negative 13. Now we definitely want to check this for whether or not it's valid because of the way that we end up solving this. We had to combine two logarithms together and we had to take a square root. So that's like two different things that could change our answer. So start with x equals 5. Five plus 4 is 9. 9 is positive. So 5 is valid. Negative 13. Negative 13 plus 4 is negative 9. Can we take log of a negative 9? No. Log of negative 9 does not exist. You can even just put that on their calculator and it'll give you an error term. So we can rule out x equals negative 13 and say we only have x equals 5. Okay. Now getting to this point where we have x equals 5 and x equals negative 13, that would give you like 9 out of the 10 points in the problem right there. The last point though is making sure we only have one valid answer, or checking for validity basically is the last 10% of the problem. That was pretty involved. Okay, 26. Log, what is that base? Is it 6? I believe that's log 6. Yes. Log base 6. Of x plus 4 plus log base 6 of x plus 3 is equal to 1. This is actually a lot like our last problem where we have two logarithms on one side equal to a constant on the right. This time the logs are added and we don't have any coefficients, so what should we do first? Right, we can combine these by multiplying the terms inside. So we know we're going to get log base 6 of x plus 4 times x plus 3. We actually don't have to carry out that multiplication just yet. Let's do our conversion first. I usually prefer to, again, that's just my preference, but I usually convert it and then I go through with the multiplication. But it actually doesn't matter. Whichever step we want to do it at is fine. Yeah, we have a log base 6. We have a logarithm equal to a number, so we are going to have to convert this at some point. What is our what does this look like when it's converted? What's our next line? 6 to the 1 equals x plus 4 times x plus 3. Good. Okay. Yeah, again, take our base to the opposite side equals the argument. So 6 to the 1 equals all that. 6 to the first power is just 6, and if we FOIL this on the right hand side, that's x squared plus 7x plus 12. What do you think we ought to do after that? Our goal is to still solve for x, and we find ourselves with a quadratic equation. Basically back at where we started this course. Factor on the right. Is there something else we should do before factoring? Something very critical that we need to do. We want the left-hand side to be 0. Yeah. Factoring and solving won't give us the right solution if we don't have 0 on the opposite side. So it's actually a nice time to kind of remember this, because as we get closer to the final, because that will certainly be relevant. Okay. So I subtract our 6, so that is just plus 6 afterwards. And I don't know what I'm doing moving this around. That was okay where it was. Let's bring this up here. So now we need two numbers that multiply to 6, positive 6, and add to positive 7. What two numbers would those be? 1 and 6. Good. So we get x plus 1 and x plus 6. So x equals negative 1 and negative 6. Good. But the question is it really negative 1 and negative 6? Let's plug in x equals negative 1. Negative 1 plus 4, that's positive 3. Can we take log of a positive 3? Yes. Negative 1 plus 3, positive 2. Again, we get a positive number, so that's good. Log of a positive number exists. Now, in this case, where we have two logarithms, our number has to check in both of those. If it works in one but not the other, then it doesn't work. Okay? But negative 1 is valid. Negative 6, however, negative 6 plus 4 is negative 2. Log of negative 2 doesn't exist. We can X out negative 6. If it fails one, then we don't even have to check the other. So we actually only have one legitimate solution here, which is x equals negative 1. All right. Any questions? That's good. That's good. That's where we want to be. Okay, I think that'll be good practice right there. So look those over. We'll wrap up this section on Monday, and then I have a little bit to cover from Chapter 7 on Monday, and that'll be the last of our work with this. I will I'll make sure I post the review today in case anyone wants to look at it over Thanksgiving, the final exam review. So, and we'll go over that exam review. Any questions on next Wednesday? Test 3 will be ready over Thanksgiving. So whenever I get it done over Thanksgiving, you'll see the grade pop up in your Canvas. So. All right. Well, you all enjoy Thanksgiving. Whether you're here today or you're watching later, that's fine. I hope you had have a good Thanksgiving, or if you're watching this after Thanksgiving, I hope you enjoyed it. Take some time to get some rest and just take care of yourselves, and I'll talk to you again Monday. Have a good one. Bye.